Alcohols, they undergo either elimination reactions or substitution reactions. Alcohols are different from alkaloids because they cannot have elimination and substitution at the same time. The reason why is because of the reagents that we use for elimination and substitution. With alcohols, the reagents are completely different. So the one that you use for elimination is different than the one that you use for substitution. This is why elimination and substitution, they do not happen together. It's either you have elimination or you have substitution. Another thing with alcohols is that the OH. This OH that you see is a very bad leaving group. So in order to make it a good leaving group, you have to make it a weaker base. We know that OHs are strong bases. So to make it a weaker base, you have to protonate. Protonate means add a hydrogen. To add a hydrogen, your reagent has to be an acid. So any reaction that you want to react with the alcohol has to be an acid so that it will protonate the oxygen. It either has to be a Bronsted and Lowry acid or a Lewis acid, some form of an acid so that it can either protonate the oxygen or introduce a plus charge to the oxygen so that it can make it a better leaving group. When oxygen is in a form of a lone pair, this is basic. And the stronger the base, the bad the leaving group. So this is why you have to introduce a plus charge on the oxygen to make it a weaker base and a better leaving group. The weaker base of the OH is water. Now, throughout this chapter, we're going to see that not just water is a weaker base. Any form of an oxygen with a plus charge in there is considered to be a good leaving group and a weaker base. So let's start with the elimination of alcohols. There are two types of reagents that we're going to do for elimination. And we said that elimination are different than substitution. The reagents that we use for elimination is completely different than the reagent that we use for substitution. So for elimination, you need a strong acid. And the acid that you want to use is an acid that does not produce a good nucleophile because you're doing elimination, you're not doing substitution. The acids that we're going to use are sulfuric acid, phosphoric acid in there. All of those, these are strong acids. When they lose their hydrogen in the first step of the protonation of the oxygen, they both form conjugate bases. These are bases, they are not a nucleophile, so that the reaction will proceed by elimination and not substitution. Another type of acid is the paratoluene sulfonic acid. We abbreviate this as a TSOH. In there, this is a strong acid in there. Again, when this one loses its hydrogen, it becomes a conjugate base. This is not a nucleophile, so the reaction will proceed by elimination. So we have these Bronsted and Lowry acids, the three of them that we can use for elimination. And then we have the Lewis acid here. This Lewis acid, the POCl3, this is phosphorus oxychloride. This is a Lewis acid that complexes with the OH of the alcohol in there and introduces a plus charge so that it can make the OH a better leaving group. This guy over here proceeds also by elimination, but the difference between the phosphorus oxychloride and the other three reagents is that this one reacts by E2 elimination only. It does not react by E1, just by E2. Alkaloid, the type of the alcohol doesn't matter. It reacts with any type of alcohol, primary, secondary, and tertiary. So we're going to take this acid here as an exception, that it works with every single type of alcohol, and the mechanism should be an E2 mechanism. We're not changing the fundamentals of the mechanism. So whatever you learned for the E2 mechanism is going to stay. Whatever you learn for the E1 mechanism, also the mechanism is going to be exactly the same. Nothing is going to change in this case. Now, what determines E1 or E2 for these acids in here, these Bronsted and Lowry acids, is the type of the alcohol that we work with. So for POCl3, we don't care about the type of the alcohol. Any type of alcohol is going to work by E2 elimination for this type of Lewis acid. For the other three types over here, no, it matters. And the rule says that if you are working with a primary alcohol with these acids, then the mechanism is an E2. If you're working with secondary and tertiary, then the mechanism is E1. Now you notice that this is different than alkyl halides. With alkyl halides, we cared about the nucleophile in there, we cared about the type of the base. This was the one that drives the reaction towards E1 or E2. But with alcohols, no. What drives the reaction for E1 or E2 is only the type of the alcohol. If it's a primary, it's immediately an E2 reaction, and if it is secondary or tertiary, it is an E1 reaction. So the reaction is going, this is going to be an example over here. Every time you use an acid, acids are exothermic. So this is why you have heat in there. Whether the heat is written in the reaction or not, heat is there. So the moment heat is produced, this means that elimination happens. And in this case here, I am losing water. So water needs to be in my product in there. What I am losing is the alpha OH and the beta hydrogen. So it's still the same idea in there. The only difference in the reactions of the alcohols between alcohols and alkyl halides is the first step of the reaction. Because you're using an acid in there and OH is a bad leaving group, you have to protonate first, make the OH water, and then the reaction is going to proceed as usual. So this is a primary alcohol in there. Start by writing the Lewis structure of the sulfuric acid. The first step is the protonation of the oxygen. So we call this a protonation step. Now you formed a good leaving group. This is a better leaving group than the OH. This step is a must for all alcohol reactions. No matter what reaction you do, every time you want to do an organic reaction, whether elimination or substitution, the first step has to be a protonation by an acid somehow. The acid here needs to have a conjugate base that is not a nucleophilic. And the conjugate base that I am getting here is the HSO4 negative. This guy is a conjugate base and it is not a nucleophile. This is why the reaction proceeds by only elimination in there. So this is a conjugate base. So in the next step, I'm going to take that conjugate base in there. And as usual, we know that it's the E2 step is one step in there. So that base is going to come attack the hydrogen, form a double bond, and water is going to leave. It's going to attack the beta hydrogen in particular in there. And you're going to end up getting your alkene. Since it's a primary alcohol, it's going to be just one product in there. So E2 reaction happens with only primary alcohols, not secondary, not tertiary. If you are dealing with secondary and tertiary alcohols, then with this type of acid in there, so the reaction is going to go by E1 and not E2. The reaction can go by E2 if you use the Lewis acid phosphorus oxychloride. In this case, yes, no matter what the type of the alcohol that you are starting with, primary, secondary, or tertiary in there. So this one needs to be a tertiary since we have the secondary. So primary, secondary, or tertiary, then the reaction is going to proceed by only E2 elimination. We've learned in the second chapter the reactions between Lewis acids and Lewis bases. So this guy is a Lewis base. It's a Lewis base from where? It's the Lewis base from the oxygen in there. So whenever you have a Lewis base and you have a Lewis acid from the phosphorus in there, try to write the Lewis structure for phosphorus oxychloride. So now the reaction is going to be from the lone pairs of the base towards the acidic site of the Lewis acid, which is the phosphorus. This is the electrophilic site, which is the electron deficient site in there. You're going to make a complex between the oxygen and the phosphorus. So you're making a bond here between the oxygen and the phosphorus, and the oxygen will have a positive charge. This is what we need. We want to introduce a plus charge on the oxygen to make it now a good leaving group. See what we did? We did a complex Instead of being a bad leaving group, now it's a good leaving group in there. Plus, of course, one of the Cl's that is going to leave. This one here is not going to be a good base. So we know that Cl minus is not a good base because Cl minus is the conjugate base of a very strong acid. So this is going to be a weak base. So we cannot use this for elimination. Pay attention. This is why pyridine is a must in the reaction, and its role is to continue the E2 elimination. So you're going to take your complex in there, and now we're going to use the pyridine base to come and attack the beta hydrogen. We have here just one type of beta hydrogen. The other type of beta hydrogen on this carbon is the same as this beta hydrogen over here. So the base is going to come, take the beta hydrogen, form a double bond, and the leaving group is going to leave, and you're going to end up getting your product in this case. E1 elimination works with secondary and tertiary alcohols. So again, what drives the reaction, whether it's an E1 or E2, is to be E1 or E2 is the type of the alcohol that you are working with. And here it's a secondary alcohol in this case. The acid has to be an acid that generates a conjugate base that is basic and not nucleophilic. And we know that whenever H3PO4 loses a hydrogen because the first step needs to be protonation, then it's going to generate the H2PO4 minus. And we know that this guy is going to be a conjugate base and not a nucleophile. So this is why the reaction is going to proceed by elimination. So the first step, as usual for every single alcohol reaction, is the protonation of the hydrogen. Notice that I am writing the Lewis structure of the H3PO4. Please do that for every single reaction. You are responsible for the mechanisms for these as I am writing them. And mechanism, you need to show arrows, you need to show that bonds are forming and bonds are breaking. So the lone pairs are going to come attack the hydrogen. This is a base acid reaction, and the conjugate base is going to leave. So this is a base, so this is why the reaction is going to proceed by elimination. So in the first step, what did I do over here? I changed the OH into a very good leaving group, which is water. Now I'm going to take whatever I have together with the base and perform the elimination reaction. Now, since it's an E1 reaction, then we know that E1 proceeds by two steps in there. After you do the protonation, you will have two steps. The first step, your leaving group is going to leave. So this is exactly the same as whatever you've learned so far. Leaving group is going to leave and you're going to create a carbocation. Once you create a carbocation, just to check how stable is your carbocation, and then stabilize that carbocation by doing either a hydrogen shift or a methyl shift. If you can, here we can move from a secondary to a tertiary carbocation, and then we're going to take that carbocation and we're going to use the base in the solution. The base in the solution is whatever is left from the phosphoric acid. So this guy is going to come and attack all the beta hydrogens in there. We have two beta hydrogens, so we have a possibility of two products. Always the most stable product is the Zaitsev product, which is the more substituted alkene. And here in this case, I have both alkenes to be tri-substituted alkenes. They are tri-substituted alkenes because the double bond that I highlighted is connected to 3 carbons, and here it is connected to 3 carbons as well. Since this is the case, then both are going to be major products. Another example over here is the secondary alcohol. This example proceeds by a methyl shift. You're using H2SO4 heat. It's going to be driven by E1. Reason why? Because this is a secondary alcohol. So first step, again, do the protonation in there. So the lone pairs are going to come, attack the hydrogen, and the leaving group is going to leave. You're going to create over here your conjugate base. Now, the first step in the reaction, water is going to leave. You're going to form a carbocation, and then the methyl is going to shift you're going to form a tertiary carbocation, and then the base is going to come and attack all the beta hydrogens. Here I do have two beta hydrogens. This CH3 is similar to this CH3. So I have two types of beta hydrogens, so I'm going to end up forming my major and my minor product, and the major product is going to be the Zaitsev product, which is the most substituted alkene. So let's have another example here. We are starting with a secondary alcohol. We are using a strong acid. In this case, this is the para-toluene sulfonic acid. And the para-toluene sulfonic acid is a CH3 that is connected to the benzene. This is going to be the toluene. And because it's para, then the sulfonate is going to be para to the CH3. And you have the O and you have the hydrogen. This is a very strong acid, and it's this group over here, which is the TS group. So the hydrogen here is a very acidic hydrogen, and we know that we have a base in this case, which is the OH. So the first step is going to be the base taking the acidic hydrogen, and the OTS is going to leave. The OTS is going to be our conjugate base that is going to start the elimination reaction. So this is the first step, and I am protonating the oxygen to make it a good leaving group, and the OTS is leaving. So that is going to be my conjugate base. First step over here is the protonation step. So this one is the protonation step. Now the next step, I'm going to proceed by the E1 elimination. And for the E1 elimination, the leaving group needs to leave, and then the base is going to come and attack the beta carbon. So the leaving group is going to leave. And when the leaving group leaves, pay attention, if you can, do rearrangement. So this is a secondary carbocation. I can simply do rearrangement by moving the adjacent hydrogen all the way to the positive charge. And now my new carbocation is going to be a plus charge over here. This is going to be a tertiary carbocation. So once you form the tertiary carbocation, in this case, you're going to go ahead and use the base in order to finish up the elimination. So we're going to take the tertiary carbocation, and we're going to take the OTS minus, which is our conjugate base in the solution. OTS is a weak conjugate base because it is derived from a strong acid. So that base is going to come and attack all the beta hydrogens in there. I do have two types of beta hydrogens. I have a beta hydrogen here, and I do have a beta hydrogen over there. So this one is going to be my beta hydrogen, okay? And I do have another beta hydrogen. So this is beta 1 and this is beta 2. And the base is going to come and attack each one of these beta hydrogens and form an alkene. So the base is going to come, take this beta hydrogen, form a double bond here, or it's going to come take this beta hydrogen and form a double bond here. In both cases, I will end up getting my alkene. So the first one is going to be the terminal alkene, and the second one is going to be an internal alkene. In there, here you go. So this is going to be my minor product, and this is going to be my major product. This is going to be the Zaitsev, and it is tri-substituted versus a di-substituted product. There are additional examples in the extra problems that I posted. Please make sure that you do those problems.